Get to talk now. Okay, so I decided to entitle this talk Semantic Interoperability. What is it and why is it needed? Because there seems to be a lot of confusion as to what that actually means, semantic interoperability. So as Rigo presented previously, what we propose within CIRPASS is two ways to go from a DPP-enabled product to the place where the DPP data is stored in the decentralized DPP data repositories. And this is where the semantic interoperability layer is implemented. In other words, this is where the magic happens. And so what I want to talk to you about in this talk is the magic. So the European Commission has this very nice course, online course from 2014, defining what is semantic interoperability. The link is just at the bottom of the slide here. And they define semantic interoperability as the preservation of precise meaning. And to make things simple, I assume here, I simplify a little bit and say that syntactical interoperability is included inside semantic interoperability. Syntactical interoperability addressing formats and structure, whereas semantic interoperability addressing also vocabularies, data models, ontologies, and reference data. So semantic interoperability is achieved when there are social agreements that are reached on all of those things. So let's compare semantic interoperability versus unification. So when I have semantic interoperability, I can map from one, for example, language to another, versus if I go towards the unification approach, we all have to agree on the same language. But this is a little bit misleading, my example, because you would think that this is just a translation service, which is not at all what I'm talking about here. So if we take the example rouge maps to red, well, semantic interoperability assumes that I'm able to say that the color red is an instance of a concept that is defined as color. Okay. And I can say that color, one color has a name, it's called cherry red, and is defined as a value 13-1023 in the Pantone color system. But I can also define the same color as luminous red in another color system, the RAL color system, but here it has a value of 3024. Because I use these concepts of semantic interoperability, I can reason and say that those are the same colors or practically the same. Okay, so we understand that we need data models and ontologies. So what's the difference between the two? So a data model is a collection of entities, properties, and relationships among them, which represent a domain, a concept, or a real-world thing. So the data model contains classes, relationships, and attributes. But data models are generally designed for very specific applications. An ontology is similar to a data model, but it's more generalized. It's designed to express higher level relationships and entities than a data model. So it's designed for greater generality and expressivity. And you can use an ontology to do reasoning tasks like I just did on the previous slide, which would not be the case with the data model. But otherwise, they're very similar concepts. So why is semantic interoperability needed for the DPP system? The answer is simply reuse. Okay? The reason for this is that developing a data model, whatever data model, developing domain ontologies, developing dictionaries and classification systems, this takes a lot of time and effort. The reason for this is that there needs to be consensus, so social agreements on all of these things. So this is what takes a lot of time. So we have to reuse what already exists, okay? Converting the above into machine-readable formats and making those machine-readable data semantically interoperable is much, much less effort. Okay, so how does this work for the DPP system? Suppose we have a delegated act of the ESPR that's defining mandatory information points. So this is very sector-specific, for example, batteries. And this regulatory text can be transformed into a machine-readable ontology format, probably by commission services or others. Then, of course, I'm a brand and I want to publish my DPPs myself. We call that the do-it-yourself DPP scenario in CIRPASS. And so I want to expose my DPP data according to the ontology formats that are required, that are mandatory. And I can do that using a number of different open source tools. This is not a problem. It's probably likely that these mandatory ontologies may use a cross-sectoral DPP system ontology that would remain small and generic and simply provide a common structure among the different delegated acts. So the do-it-yourself DPP is one scenario, of course, but we've heard a lot about DPP as a service providers who would be doing this mapping for you, of course. And so me as a brand, I could simply upload my data into to their platform, and they would be doing all of that for me if I don't want to do it myself. But there's another scenario. Suppose we have an industry association that proposes to host the DPP data for all of their members. So they would be, and suppose they have a very large industrial domain ontology that is useful for them. They could be providing this alignment service using bridge ontologies, and there are many open source tools to do this alignment process. So this is not a problem either. So therefore, me as a brand owner, I would just map my data to that domain ontology. So as the DPP gets deployed across many sectors, of course, there will be future ESPR delegated acts, maybe the construction products regulation, the battery regulation, etc. Other mandatory ontologies. So they would be defined in a similar way as I expressed before. And they would be potentially using the same cross-sectoral DPP system ontologies that can grow as needs arise. For example, to define events in a common way, to define actors in a common way, to define digital units in a common way. Many of these ontologies already exist. Okay? And since there are many possibilities for implementing the decentralized DPP data repositories, like the orange circles I have at the bottom, well, this makes it possible to address sectors that are highly centralized with many large, with a few very large actors, for example, the tire industry, which is extremely different from the textile industry, which have a very large number of SMEs. So there are many, many ways that this can be implemented. If we look into the future, we can expand on this. Not, of course, right now, but we have to build a system that will be here for the next 50 years. So we can expand the cross-sectoral DPP system ontologies to address topics such as life cycle analysis, corporate sustainability reporting. So I did a quick look, I did a quick search on the internet, and there are many such ontologies that already exist. This morning, Steve talked to us about the UNTP protocol, and it would be very easy to use the UNTP ontologies similarly. And I'm a very lucky person because every week someone writes to me and says, I have an ontology for the DPP system. And so for the most recent one is a digital calibration certificate ontology that exists today and that could be reused out of the box. So in the following video, we want to put all of this into action. And so I hope that you will enjoy this, this little futuristic walk into the future.
Welcome to this demonstration video of the DataPipe project. The purpose of this video is to explore how authorities could potentially exploit digital product passport data in the future. This demo was developed in close collaboration with the CIRPASS project. This imaginary example is provided for demonstration purposes only. First, a few words about the DataPipe project. In DataPipe, we explore how authorities can access and use external business data sources for various purposes. The challenge is that this data is stored in the digital infrastructures of different businesses. In this imaginary scenario, we explore how digital product passport or DPP information could be used in customs risk analysis. For example, to address environmental concerns. Here we look at the export of second-hand electric cars, with the aim to prevent the export of end-of-life vehicles, which could be considered to be waste. First, we assume that the battery DPP is mandatory. Second, we assume that the car producer issues a car passport voluntarily. Third, we assume that the vehicle identification number, also called the VIN number, is mentioned on the export declaration. Fourth, we assume that the battery's state of health data may be one of the indicators that customs could use when deciding whether a car can be considered end of life. Finally, we assume that the battery in the car has not been changed. The imaginary scenario runs as follows. When producing a specific car, the car company orders a battery. The battery producer issues an identifier for that battery, and at the same time publishes the DPP data on its system. This data then becomes accessible, via a web link, to anyone with the correct authorizations. The battery producer sends both the battery and the link to the battery DPP to the car producer. The car manufacturer produces a new car identified by a specific VIN number using that battery. In our scenario, the car producer decides to create a car DPP that contains the link to the battery DPP. We now have two product passports that are linked together. When the car producer places the car on the market, he registers the car with the authorities by providing the car's VIN number and the web link to the car's DPP. The car is sold. The owner of the car uses it. At some point in time, the owner decides to export the car to a country outside the EU. We assume that one of the roles of customs is to prevent end-of-life vehicles from being exported. During risk assessment, one of the indicators used could be battery state of health. If the battery state of health is indicating end of life, customs may consider this car as waste and ban it from export. From the export declarations that customs receives, it has only the VIN number of the car, but no information on the battery's state of health. How can customs access this information? Let's assume that there is a data sharing system through which customs can request the data it needs. As a first step, customs uses the vehicle's VIN number to obtain access to the car DPP through the car registration authority. Thanks to the link to the battery DPP contained in the car DPP, customs can obtain battery data, including the state of health data. Customs then proceeds to risk analysis and decides whether or not to ban the car from export. While decentralized data sharing systems may require additional effort when being set up, they offer important advantages such as extensibility, flexibility, and combinability. Extensibility means that new data sources can be added to the system easily. For example, a tire DPP, an electronic systems DPP, or an engine DPP. Flexibility means that customs inquiries can be easily extended to exploit these new data sources. Combinability means that manufacturers of complex products can combine data from different suppliers into their DPP. But how does this work in real life? For the technical implementation of the data pipe demo, I made use of results of earlier projects and open source tools, and followed the steps as shown in the slide. We demonstrate that there is no need to start from scratch, and that quick progress can be made by deploying existing technologies. Here we give some impressions from the technical demonstrator. We show the use of open and aligned ontologies, sharing events via the data sharing infrastructure, and constructing APIs and querying data. The system as shown can be easily extended to many sectors by adapting the aligned ontologies and the corresponding API configurations, instead of generating and configuring completely new APIs. It is important to highlight that in the scenario we present in this video, we look beyond what is currently possible or required for customs given the current regulations. We take the view that a wealth of information is and will be available in the future. Authorities may benefit from this information for circular economy and sustainability monitoring. The flexibility, adaptability, and combinability properties of the system make it future-proof. If you are interested in the technical details of this demo, you can watch also the DataPipe developers video or visit the DataPipe GitHub page, where new demo videos will be posted in the future. Further information is available on the DataPipe website.